Good day everyone. In this video, I'm going to show you a Lagrange polynomial, linear piecewise, and cubic spline interpolation calculator through MATLAB. First, let me discuss a Lagrange polynomial interpolation calculator. This is the code I used for this machine problem. It can calculate up to n points. For the first line, this asks for the input of the t values, and here for the input of the y values. N is the length of the t values or the number of t values, and L is set to be a matrix of zeros with a number of rows and columns equal to the number of t values. Next, P naught is a t value to be interpolated. Here is where the loop begins. I is for setting up the row of matrix L, meaning for each row from 1 to n, the loop proceeds. V is the initial vector, and here it is initialized to 1. A subloop begins to set up the columns of I. This means that for each column of I from 1 to n, an if-else condition proceeds. The condition is if I is not equal to j, it should proceed to the next line. If they are equal, it should proceed to the next value of j. V is the convolution or the multiplication of vectors of two polynomials. The first vector to be multiplied is the v. We initialize to be 1. And the second vector to be multiplied is the polynomial of the jth value in the t dataset. It treats the jth value of a given dataset as a root and then converts it to polynomials. For example, if x of j is 3, so we should have poly of 3. Let's try it here in the command window and type poly of 3. You can see an output of 1 and negative 3. This corresponds to a polynomial of x minus 3 equal to 0. After multiplying the vectors, the v is then divided by the ith value of the dataset minus the jth value of the x dataset. Once all j columns in row I are convoluted in V, the row I of matrix L is then equal to the polynomial V multiplied by the ith value in the Y dataset. The loop continues until all rows in the matrix L are filled up. Let me show you an actual calculation of what is happening in this part of the code. For the loop, we have data points of 2, 5, 5, 7, and 7, 8, so that makes n equal to 3. For the loop, for this example is for I is equal to 1 to 3. So first, let's see I is equal to 1. We initialize the vector v to 1. So is j equal to 1, which is the current value of I? Yes, so it should proceed to the next value of j, which is 2. So v is the convolution of 1 and the polynomial of x of j all over x of I minus x of j. V then is the convolution of 1 and the polynomial of x of 2 all over x of 1 minus x of 2. V is a convolution of 1 and the polynomial of 5 all over 2 minus 5, and that makes V is equal to convolution of 1 and negative 5, which is equivalent to the polynomial of 5 all over negative 3. So for this numerator, this is a visualization of what happened. So the convolution of 1 and the vector of 1 and negative 5 is x minus 5 and 1, which is just 1, is equal to x minus 5, and its vector is equal to 1 to negative 5, or just the coefficient of this polynomial. Now the convolution is the multiplication of two vectors. Now the vector is now multiplied with negative 1/3, and that makes v is equal to a vector of negative 0.3333 and 1.6667. For the j of 3 and still I is equal to 1, v is a convolution of the vector we got from j is equal to 2 and the polynomial of x of 3 all over x of 1 minus x of 3. V is then the convolution of the vector we got at j is equal to 2 and the polynomial of 7 all over 2 minus 7, or the x of 1 and the x of 3. So from here, v is a convolution of the vector we got from j is equal to 2 and the vector 1 and negative 7 all over negative 5. So again, in this numerator, the visualization of the calculation is like this. So the vector of 1 and negative 7 is equal to x minus 7, and the vector of negative 0.3333 and 1.6667 is this. So if we multiply these two multiplication, we have this polynomial, and the coefficients of this polynomial is this, and so we got this vector, and this is then multiplied by negative 1/5 from our denominator here. So the vector is now 0.0667, negative 0.8, and 2.3333. So since y of 1 is equal to 5, and L of I, so that means the row I of matrix L is equal to V times the y of I. So let's multiply this vector with our y of I, or 5. So that makes it like this. And now the first row of our matrix L is this. And for the I is equal to 2, our matrix becomes this. And finally, for the I is equal to 3, the matrix L is now all set up. Now P is the summation of L. Now if you sum these vectors or matrix, we will have a polynomial of negative 0.0333, 0.9, and 3.3333. So this is just the coefficients of our interpolant. So that was L, or the matrix L, and the P, or the sum of L. To print the polynomial, we have to flip the coefficients of polynomial P and create a loop. This loop means for k is from n to 2 incremented by negative 1. So this is basically for the exponent of the polynomial. This is for the format code, and this means 8 decimals of a floating number f, and d is an assigned integer. These are all code languages in MATLAB. Now the floating number f is assigned to f of k, which is a kth value in the vector f, and d is assigned to k minus 1 for the exponent. This line is to print the coefficient of the constant of the vector f, or the polynomial f. This returns the value of the polynomial p substituted by the t value to be interpolated. This is the output to display the a, or the approximate value at given data point is a. This generates 1000 points between x of 1 to x of n, or from the first point to the last point with regards to the inputted data values. This evaluates each y for the generated x using the polynomial p. This displays the plot of the generated x, y for the polynomial, and this line holds both of the plots, here this and this, which displays the plot of the given data values. This next set of code is for piecewise linear interpolation and cubic spline interpolation. Again, this is for the input data values. Here, x test is the input for the t value to be interpolated. x2 are the values from the minimum of the t data values to the maximum of the t data values incremented by 0.1. This interp1 is a lookup function to find yy from the values of the input t and y at the query points x2. And the linear here is a method of the interpolation according to the available methods in MATLAB. This displays the plot of the t and y data values, including the query points and the yy, with a circle and black for B format. This shows the grid for the graph, and this holds the graph for another plot. Y cubic spline is the interp1 or the lookup function to find y cubic spline from the input x and y at the query points x2 using the spline method, or this is the cubic spline method. This shows the plot of xy with x2 and the generated y cubic spline. The y linear piecewise, this displays the evaluated value of f of t in linear piecewise interpolation at x test, or the t value to be interpolated. And this line is the evaluated value of f of t in cubic spline interpolation. Let's run this code with our machine problem. Let's try this problem for our code. To find how much heat is required to bring a kettle of water to its boiling point, we are asked to calculate the specific heat of water at 61 degrees Celsius. The specific heat of water is given as a function of time in table 1. So this is the column for the temperature. So this is going to be our T values, and this is our specific heat, which is going to be our Y values. Let's input our known dataset. First, let's click Run in the Lagrange interpolation. We have 22, 42, 52, 62, 82, and 100 for the temperature. And for 181, 4179, 4182, 4186, 4199, and 4217 for the specific heat of water. And we have to find the specific heat of water at 61 degrees Celsius. Let's click enter. These are the matrices L used to get the polynomial P, and this is the interpolant of the interpolation using Lagrange polynomial. So at 61 degrees Celsius, the specific heat of water is 4185.5475. This is a graph for the polynomial Lagrange interpolation. Before we proceed, let's hold this graph by typing hold on. Hold on in the command window. Let's input the same data set in the piecewise linear and cubic spline interpolation calculator. First, let's click run. Then 22, 42, 42, 52, 62, 82, 100 degrees Celsius, 4181, 4179, 4182, 4186, 4199, and 4217. Then let's click or type 61 degrees Celsius. So the generated Y linear piecewise or the interpolation at 61 degrees Celsius using linear piecewise is 4185.6, and using cubic spline we have 4185.5. So let's look at their graphs. Now we have the plots of the three methods of interpolation. So the red here is for the Lagrange polynomial, the violet here is for the cubic spline, and the red here is for the piecewise linear. When we plot the given values, we can see that it decreases from 22 to 42 degrees Celsius and increases from here on. From this case, both cubic spline and Lagrange polynomial interpolation gave reasonable results because of the smoothness of their graphs. However, for Lagrange polynomial at higher degree, the graph tends to oscillate further, making them unfit in evaluating interpolant at any given point. I say that cubic spline gives the most reasonable data out of the three because it is continuous at second derivative, making it the most smooth, and it is flexible because of the use of intervals.